Welcome back. It's day 3 on the eventually 10 different tests for proving series convergence or divergence. Today we're going to talk about 2 different types of tests, the integral test, and it'll lead us straight into the p-series test. So you've got a notes page. I'm just going to walk through those examples and work these examples with you, and then assign some homework in my math lab to tie in some practice with that. So the way the integral test goes, much like many of the other theorems that we've learned, you have to think about the conditions first. So we'll start with that. If f is positive, we have a positive function that is continuous and also decreasing. Okay, so f is some function that's positive, continuous, and decreasing, and you'll see me address that for each of those values. For values greater than x is greater than 1. Okay, greater than or equal to 1. Okay, because you'll see we've got an integral here. If a sub n is our function of x, so the series terms a sub n is our function of x, then the sum of that, the series, right, the sum from n equals 1 to infinity of a sub n, and the integral from 1 to infinity of that function. So we're comparing a series now with an integral, the area under the curve, with its series. If they are they're both going to either converge or they'll both diverge. So what we can do is make conclusions about the series based on what the integral is from 1 to infinity. So if this integral converges, then the series is going to converge. If the series diverges, then the integral diverges, then the series is going to also diverge. Okay? Then we can say furthermore that if the series does converge to some sum s, then the remainder of that, so we've got some sort of a sum there of, let's say, the nth remainder, and we'll see an example that we'll talk about this, that's going to be bounded by this this interval here. So the remainder, the error, so to speak, is going to be bounded between 0 and the integral from the 7th term. So that, let's say the 7th remainder would be from the 7th term on to infinity. We'll see that as we go. So let's try this first one. Again, you first need to check the conditions. So I'm going to go through those rather quickly because we're not going to make it a formal proof, but we still need to think about that. Is n over n squared plus 1 for all values of n, where n is 1, 2, 3, etc., is that going to be a positive? And I think that would be true. Okay, we could show that and think about that and think about that condition. A positive number divided by a positive number is a positive number, basically. Okay, so that's our first condition. Condition 1, that it's positive. Continuous. Well, would this be a continuous function? Again, you're thinking about, well, I see a fraction. Are there any vertical asymptotes? No, no vertical asymptotes. It's a ratio of 2 polynomial functions that would be continuous, so there's no problem there. And would that be a decreasing function? So think about that. Would the next term be decreasing? Well, one thing we could do is take the derivative, right, and show that that derivative is negative for all the values of that. We're not going to make it that formal, but if you think about a value divided by an ever-increasing value, right, n over n squared plus 1, right, that's not going to make a big difference there. But n over n squared, those should be decreasing as the function, as the value of n gets bigger. That should be a decreasing function. But if we had to prove that formally, then we could take the derivative and check the values there for n greater than 1. Okay, so we've checked our conditions. It is positive, continuous, and decreasing. Why would we want to do the integral test for this? Well, I'm looking at this and instead I'm thinking, what if I did the integral from 1 to infinity of n over n squared plus 1? And we could make that dn, or we could just make this x values, right? So you won't do x because we'll do a function of x. So we'll instead write that as the area under the curve from 1 to infinity of x over x squared plus 1 dx, and that seems to make sense. All right? And sure enough, we would take the limit, because it is an improper integral, the limit as a approaches infinity from 1 to a of x over x squared plus 1 dx. Got to figure out first our integrand and what that antiderivative of that would be. Well, it kind of looks like u prime over u. Let's try it. U equals x squared plus 1. Du would be 2x dx. So I need to squeeze in a 2. Need to squeeze in a 1/2. And we would get the limit as a approaches infinity of 1/2 natural log absolute value x squared plus 1, and evaluate that from 1 to a. Okay? Well, if I plug that in, I'd have 1/2 log of, well, plug in our upper limit there, right? Wouldn't that be, in fact, I could squeeze in the limit one more time here. Limit as a approaches infinity. 1/2 log of a squared plus 1. Wow, that's a pretty big number there. Minus 1/2 natural log of 2. Well, 1 plus 1, 2. Yeah. What is that limit there as a approaches infinity? That's going to be infinity. Okay? Therefore, since the integral goes to infinity, the integral diverges, therefore we're going to say that the series, and here our series, is that sum term, so it would be n equals 1 to infinity, n over n squared plus 1, also diverges by the integral test. Okay? So we're comparing an integral to a series, and since this integral diverges, then the corresponding series would also diverge. This one looks a lot alike, but it's 1 over n squared plus 1, not n over n squared plus 1, the series of that as n goes from 1 to infinity. So again, quickly, just check those conditions. We're not going to dwell on those, but we need to check that. 1 over n squared plus 1, that is positive, right? Because all those values would be positive. That would be continuous because there's no vertical asymptote there for n squared plus 1. And it would be decreasing because as n gets larger, we're dividing by an ever bigger number. So each of those terms in our series is going to be getting smaller, decreasing. Okay, so we've checked that. Now we're going to do the integral from 1 to infinity of 1 over x squared plus 1 dx. Well, again, improper integral. Limit as a approaches infinity, 1 to a of 1 over x squared plus 1 dx. And I know we all recognize that as arctan, don't we? So I'm going to say that's equal to the limit as a approaches infinity of arctan of x, right? Because it's just a real simple one. U squared is x squared, so u is equal u squared equals x squared, u equals x, du equals dx, so check those, right? And a squared is 1, so a is 1, 1 over 1, yeah, so x over 1, u over, yep, we got it. Arctan from 1 to a, arctan from 1 to a. Well, that means the limit as a approaches infinity of arctan of a minus arctan of 1. Not all of these are going to be infinity, right? In fact, it's asking you what angle has a tangent of positive infinity. What angle has a tangent of positive infinity? Well, using your vast knowledge of the unit circle, he says you still have to have that vast knowledge, is pi over 2 there, minus arctan of 1. What angle has a tangent of 1? We all know that. Minus pi over 4. So pi over 2 minus pi over 4 is pi over 4. That's finite. Before, the first example, it was infinite, so these series diverged because that's an infinite. Well, since this is finite, therefore, our series converges. The integral acts the same as the series and vice versa. So the series converges by the integral test. Any questions, let me know. Email me or message me. Okay? The series converges by the integral test. All right. We mentioned before up top this other bit where we've got the remainder. So let's talk about that. Approximate the sum of the convergent series using 6 terms. They're telling us this is convergent. We'll show this later that it is convergent. We'll see that. But using 6 terms, well, n equals 1, n equals 2, n equals 3. So remember, a series, all we're doing is adding up each terms until we run out of terms. So from 1 to 6, using 6 terms. So I've got 1. In fact, if you need the n equals 1, 2, 3, 4, 5, 6, just to make sure that you get them all right, use those n values as your counter. 1 over 1 is 1, plus 1 over n to the 4th. Well, to the 4th. 1 over 2 to the 4th, plus 1 over 3 to the 4th, plus 1 over 4 to the 4th, plus 1 over 5 to the 4th, plus 1 over 6 to the 4th. All right? So we've got those terms there. Well, that would be 1 over... Would you probably want a calculator for this? Yes, I agree. So I'll just write these numbers down real quick. 1 over 81 plus 1 over 256 plus 1 over, what is that, 625? Plus 1 over 6 to the 4th, 1296. If you had a calculator, that would be 1.0811253. Notice how I'm giving you more than 3 decimal places because this is an interim number, okay? Now, this is a approximation of the sum. If you had a final answer, you would give it in 3 decimal places. But we want to include an error estimate. So a lot of times when we talk about an error, we're hoping that it's at least accurate to 3 decimal places. I mean, yikes, that's pretty small. Okay. How would we find that remainder? Well, the remainder is everything from that point, okay? So instead of finding the integral from 1 to infinity, we're going to find the next of the remainder. So the remainder of the nth term is 6. Here, I've got 6 terms, so I'm going to do the integral now. Whoops, so you can see me here. 6 to infinity of 1 over x to the 4th dx. Alright, so I'd write that again because we've got an improper integral. Limit as a approaches infinity, integral from 6 to a over x to the negative 4th dx. Right? Increase the power, divide by the power. Negative 1/3 x to the negative 3, evaluate that from 6 to a. Okay, so if I plug in my upper and lower limits, I get the limit as a approaches infinity of negative 1/3. And since that's a negative exponent, I think it'll be easy if we see this as a to the 3rd. Well, negative 1 over 3 times a to the 3rd, isn't that going to be pretty big? Yeah. Minus negative 1/3, 6 to the 3rd. And again, since we've got that as a negative exponent, I'm just going to move that down 6 to the 3rd there. So minus would be 1 over 3 times 6 to the 3rd. Or, and this would be fine if you left that as your answer, but if you had a calculator, you could clean that up. 1 over 648. Okay? So our remainder then is anywhere between, so 0 is less than, our remainder is less than or equal to 1 over 648. That decimal form is 0.001543, by the way. A few decimal places, 0.01543. Yep. So your final answer then, it's not off by much, right? 0.0015, 0.0015. Yeah, you're good there. All right, so that's the remainder for the integral. So it's not off by any more than that. It's pretty accurate. And that's the thing that we're going to see, especially when we get into the Taylor polynomials. The more terms you add, the more accurate it's going to be, but there comes a point where it's diminishing returns. You're doing a lot more work to get to the next term as far as calculations go. Because remember, this was all developed back when we didn't have calculators. So they needed ways to get accurate answers and evaluate and take derivatives of functions that were easy to take derivatives of, instead of having uglier functions. So using that remainder idea, for many applications, that would be more than enough. Maybe just the first 3 or 4 terms would be plenty, depending on how accurate your answer had to be. All right, so there's the remainder, and we'll see remainders more. Alrighty, p-series are going to be a big one, so we need to make sure that we think about these. Okay, a p-series would look like this, and that last one was one that we just did as a p-series. We had n to the 4th power. But we've got the sum from n equals 1 to infinity of 1 over n to the p power. So 1 over 1 to the p, 1 over 2 to the p, 3 to the p, etc., etc. This is called a p-series, where p is going to be a positive constant. A special one, when p is equal to 1, that series is called the harmonic series. So please put a star by that word. I would expect you to know that word. Harmonic series is going to be a big deal. Okay? So first thing that we're going to think about is different values of p. So we're going to go ahead and do that harmonic one right now. Again, we're not going to dwell on it, but we should at least check and confirm that this is positive. So when p is 1, it'd be the sum. And if you want to expand those out, it would be 1, when p is 1, or when n is 1, it'd be 1 to the 1 plus 1/2 plus 1/3 plus 1/4 ... because it's an infinite series there. But that would be positive. All those terms are positive, and you can see it. Look, expanding out those terms, I think we can see that that would be positive. There's no vertical asymptote, so it's continuous, and those terms are decreasing, so that function overall would be decreasing. We can use the integral term. So the integral from 1 to infinity of not 1 over p, but now, or 1 over n to the 1, would be 1 over x dx. Well, what's that integral? Do you recognize that one? I'm going to write that limit as a approaches infinity, 1 over a, 1 to a of 1 over x dx. Isn't that the log? Yeah. The limit as a approaches infinity of natural log of x evaluated from 1 to a equals, well, golly, isn't that the natural log of infinity minus the natural log of 1? And we all know the natural log of 1 is 0, but what's the natural log of infinity? Oh yeah, that's infinite. Therefore, that's infinite. It diverges. So we're using, and this is kind of cool, we just use the integral test to prove what we're going to conclude down at the bottom here in this table here. I'll scroll down for you to see that. We're going to summarize all of those. We're using the integral test to create a new test. So this will be a shortcut here. All right, well, let's find it when p is 1.1, because it's a little bigger than 1, and then we'll compare it again with 0.9. Same idea. Those are positive, continuous, and decreasing when x is greater than 1. So I'm going to set up my integral now from 1 to infinity of x to the negative 1.1, right? Because that's the same as 1 over x to the 1.1. So x to the negative 1.1. So we can use the power rule. Well, that's the limit as a approaches infinity. Integral from 1 to a of x to the negative 1.1 dx. All right. Well, if I increase the power, divide by the power, what's your new power? Isn't that going to be the limit as a approaches infinity of negative 1 over negative 0.1? Increase the power, divide by the power, x to the negative 0.1 from 1 to a. And if that looks kind of confusing, I agree, decimal places and all that. If you rewrite this limit as a approaches infinity, well, negative to negative are going to cancel out. That's okay. 1 divided by 0.1, well, that's the same as 10. And negative exponents, isn't that just going to be x to the 0.1 power? So 10 over x to the 0.1 power. Wait, this is not a negative here, is it? Increase the power? Yeah, that would be. I think that would be. Yeah, that's right. We're good. We're good. So 10. Where am I making my mistake? I doubled my negative number. Yeah, so this is positive. This here, I just moved the negative sign up, so I do apologize. This is going to be a negative still, so that's still true. So increase the power. I just put the negative, so we didn't. Sorry about that. In an ideal world, I would record this, but you know how making mistakes in the math. Check your work as we go. So I'm not going to take the time to record it. I want to make sure that we keep rolling here. So increase the power would be a negative 0.1, but I just moved that negative sign, so it's negative 10 over that. Let's evaluate that then from 1 to a. Yep, is the limit as a approaches infinity of negative 10 over a to the 0.1 power minus negative 10 over 1. Right, plugging in a 1 because 1 to any power is handy. That's 1. Okay. This is going to be negative 10 divided by a very large number, even though it's the 0.1 power, right? So that's going to be 0 minus plus 10, right? Because negative negative makes that 10. That equals 10. Okay. That converges. Right? That series converges because when p is greater than 1, it would appear that using that 1.1 as a test is going to be greater than 1, and that works. All right? The next one. Let p be 0.9. So same arguments before. Is it continuous? Yes. Is it positive? Yes. And is it decreasing? So we'll set up our integral from 1 to infinity of x to the negative 0.9 dx. Well, improper integral, set up our limit again, limit from 1 to a of x to the negative 0.9. We'd get the limit as a approaches infinity of, let's see, 1 over increase the power would just be 0.1, so that'd be that. X to the 0.1, so it's not a negative power, it's a decimal there, from 1 to a. That equals the limit as a approaches infinity. Well, 1 over that is going to be 10, right? 1 over 0.1 is going to be 10. A to the 0.1 minus 1. So a to the 0.1 is going to be infinity minus 1. That's going to diverge. Therefore, the series is going to diverge using the integral test. Why did we do all these? Well, now we have proven this, so this is the one that I want you to know. So let's put a star by this one. P-series are going to be an important one that we need next time around too. In the first case, we just saw it's equal when p equals 1. The series is going to diverge. And we said that that was an important one to remember the name. That's the harmonic series. So when it's exactly equal to 1, it's going to diverge. The series is going to converge when? Well, that was this example here, the second one. When p is greater than 1. And it will also diverge when p is less than 1. In fact, we should make it 0 is less than p is less than 1, because we're not going to have a negative p value. These are always going to be positive values there. If it was a negative, it would make it just a 1 over that, and that would fail the nth term test. That would diverge because of nth term, not because of the integral test, not because of the p-series test. So you can kind of see that these kind of interrelate as we learn more and more of these rules. This, by the way, is test number 5. I've kind of added those up as we go. This is test number 5 that we need to think about. So we're halfway through our series of 10 tests. Why is this example here? That certainly doesn't look like a power to me. Well, can you rewrite it as a power? You've got the sum equals 1, or the series from 1 to infinity of 1 over n and n to the 1/2 power, right? So would be n times n to the 1/2 power. And then just the sum n equals 1 over n to the 3/2 power, right? Because you've got n to the times n to the, you add the powers, so n to the 3/2 power. Well, this is definitely a p-series, so you'd want to identify that with what? P equal to 3 over 2. There's your power right there. Okay, which is greater than 1. So given that summary, so now we don't need the integral test. Why waste our time when we've shown that the p-series test is going to be working? Well, if p is greater than 1, our series is going to converge. So series converges by p-series test. Okay, so we learned 2 new tests today. The integral test, which was powerful for in its own right, but also powerful for creating the p-series, which will be one that we need to use going forward. That's why we put a bigger star by this one than the integral test, especially if as we look forward to the AP test in the condensed version, that we'll see those. So I'll kind of, as I learn more about that, I'll get more of that to you. I just want to cover all these 10 tests, and then we'll kind of digest as they release more information. All right, that is the lesson for day 3. If you have any questions, please be posting me messages on Canvas. Email me. Also, pay attention to the calendar. I've set up conference times from 8 to 8:30. Since I have 3 different preps, A, B, B, C, and multivariable, I've assigned days for conferencing with you from 8 to 8:30 on certain days. So make sure that you pay attention to those, and we'll be able to chat and go over any questions. And also look on my math lab for any daily practice that we'll assign. And quiz coming. The daily practice is not required. It's for your review. The quizzes and tests that will be in my math lab are required. That's how you're going to get your grade for this 9 weeks term. All right. Again, hope everything's going well. And also, if you're having any technology questions or anything that I can help you with, please let me know. If it's actual hardware questions and needs, please make sure that you're getting a message to your counselor. They're the ones that are charged with getting and lining up technology and helping you out with any issues that you might be having there. Hope everything's going well, and I will talk to you very soon. Have a great day.